Hey physics kids, Mr. Johansson here. I have a demo here for you I want you to see. So sorry I had to put you in the back of the room. It's not like you were being bad or anything. I just got to do the demo way up in front, so you got to see the whole thing. This is all about uniform circular motion. So check this out, all right? This is a cup of water. I want to make sure you see it is clearly a cup of water. There is no cover on it. It is just water inside. If I tip it, it will spill. That's an important thing to know. This is the lid from a 5-gallon bucket. Granted, it's stupid, but I put string on it in a way that makes it level. Sort of. I'm going to take this water and I'm going to set it right on top of the bucket. Now you see there is nothing connecting this. As a matter of fact, there's bumps on the bucket that keep the water cup from sitting nicely on it. So there's no trickery here other than physics. So the idea here on this waiter's tray is that if you can see me flipping this back and forth, you see that the cup, the water stays perfectly level in the cup. No matter how I do this, the water stays nice and level. That's pretty cool, all right? So the water doesn't come out of the cup. Even if I make pretty big arcs with that. Look, the water stays perfect. And if I, ooh, that always gets them. I hope you're going, ooh, something like that if you haven't seen this before. All right? No, even upside down, the water stays perfectly in the cup. Now, watch. Yes? Like you're going to look away anyway. All right, pay attention. As long as I don't let this go, that water stays in the cup. It doesn't come out. All right, so how can that be? What's going on with this cup of water that keeps the water held to the bottom, just like it is now, even when the cup is turned on its side? And with this water, we could talk about this for a second. All right, so let's talk about this. When the cup is down, what's holding the water in? Good, gravity. The water would like to accelerate down at G. I'm holding it so it can't. So the water is pressed into the bottom of the cup. Great. What's the situation when the cup is tipped like this when I'm spinning it? What's going on? What's the only motion of this cup that would hold the water in the bottom of it? Think about that. If I move the cup at constant velocity, here, would you like a cup of water? The water's going to spill out. Even if I move it at a fast constant velocity, here, have a cup of water, the water spills out. But there is a motion that will press it into the bottom of it. Imagine you're in an airplane about to take off, if you had this experience. When the pilot puts the throttle all the way forward and releases the brake, all of a sudden this plane starts accelerating forward. Accelerating. It's not at a constant velocity. That thing is at zero and it's trying to get up as fast as it can, as quickly as it can. So that's one of the biggest accelerations you're ever under in a normal situation. How do you feel? You are pressed into the back of your seat. Well, yeah, pressed into the back of your seat. Just like the water is pressed into the back of this cup. So what is this cup doing? Yes, it must be accelerating. If it's not accelerating, the water's going to fall right out of it. So the water didn't fall out, so this must have been accelerating. Which way? It must have been accelerating that way. Sometimes people are confused. They say, oh, it's accelerating that way. Fill the cup with water, accelerate it that way quickly. See how that works out. Right? So, no, that's not what's going on. The cup is accelerating that way. When it's upside down and the water is still pressed into the bottom, which way is it accelerating? Yeah, it must be accelerating down. How about this way? Must be accelerating that way. Can we characterize how these accelerations are? Yeah, they're all towards the center of the circle. They're all towards the center of the circle. So come on up here, let's talk. Let's go to the board, shall we? Uniform circular motion. All right? So we're talking all about uniform circular motion. The formulas on this are pretty crazy easy, but there's some ideas on it that are pretty crazy important. So let's first draw the circle. So we have the cup. In each case, and it must be accelerating towards the center. Right? The cup has to be accelerating towards the center. What do we call this? We call this center seeking acceleration. But we're science people, so we got a better name than that center seeking. I mean, really. So we call it centripetal acceleration. Centripetal acceleration. Ooh, okay. Well, that's different. You've probably heard of centrifugal acceleration and centrifugal force. You're driving in a car, somebody turns the wheel to the right, and everybody in the car flops over to the left. And when you say, "Why? What is that? I'm flopping over to the left. What's that?" And somebody says, "Oh, that's centrifugal force." No such thing. From outside the car, when you're looking at people driving, you see the car turn to the right, and the people want to go straight. How do the people end up going to the right? The car has to smack into them and push them around to the right. They never flopped over. They were going straight. The car flopped into them. It was just inertial. But now let's go to the car flopping into them, the car pushing into them. They were going forward. Now they have a force at right angles to the direction of travel, and they will start going around in a circle. Centripetal acceleration. What causes an acceleration? An unbalanced force. What causes a centripetal acceleration? A centripetal force. A centripetal force caused the centripetal acceleration. Now, in the waiter's tray, I was just spinning around. Am I applying a force on that string? Well, you bet. If you're not quite sure, put a third grader on that tray and go ahead and sit there, good, and try to flip them around. Yeah, there's a lot of force on that string. And what's pulling them is centripetal force. They're moving at right angles to the direction I'm pulling. And so I'm pulling them completely around in a circle over and over again, right? When you look in your reference tables at the equations, some stuff to talk about there, okay? The equations are at this point, the equations are just absolutely simple. A sub c, acceleration centripetal, equals v squared over r. Now that is a simple formula, but there's a little bit to it. As a young guy, I was driving to New Paltz and went around a hairpin turn. It said 5 miles an hour, and I hit it at 20 miles an hour. That's 4 times the force I was supposed to hit it at. This v squared is what causes some trouble. So let's put it in the force equation, and you'll see why it caused me so much trouble. All right? The very next formula in your reference table says F sub c, force centripetal, equals mass times A sub c. Well, now they're just being a pain in the butt, because they used to put down the complete formula, but what they want is for you as a physics student to have absolutely no trouble with substituting and building a new formula. So what are you supposed to substitute? Substitute for AC, what AC? A sub c equals. So we get rid of the A sub c and we put v squared over r. And that would be the complete formula. So when I hit that turn 4 times faster than I was supposed to, how much more force did I need to stay on the road than the engineers anticipated? Well, if we just say F sub c is proportional to v squared, and I put 4 in because I was 4 times the velocity I was supposed to, what kind of force? Well, what's 4 squared? 16. I hit with 16 times the force I was supposed to. And that very nearly caused an accident. I had no idea what happened. But what I learned in that moment, I'm not a stupid guy. Doesn't feel like it. Might not be that smart, but I'm not a stupid guy. But I realized I'm missing something. And I'm missing something important, and I bet you are too. Turns out all of us seem to be misprogrammed when it comes to velocity. In my head, and I suspect in your head too, if I'm going twice as fast, I'm going to hit something and have twice as much force exerted on me, not 4 times. But in the real world, what we find, it's not proportional to your velocity. It's proportional to the square of your velocity. So twice as fast gives you 4 times the force. Because we're not programmed for it, a lot of people when they're driving are going way too fast in their maneuvering and doing all the things they do. And then at an early age, they very often don't make it. The V squared is a very dangerous thing because we don't get it. In an earlier video, I tried to explain how we get F equals ma, force equals mass times acceleration. You get every aspect of that. You wouldn't make it here safely without knowing that. But the V squared thing, we don't get. And that's the reason so many people don't make it someplace safely. They simply go too fast. That V squared is deadly. So I have a personal relationship with this V squared. Don't like it very much. Almost took me out, but it's taken way too many others. So the solution for all of these things is very straight up. There's not a lot of hard stuff. Let me show you the only hard thing in this whole schmear, all right? And it's not physics, it's geometry that you're gonna find difficult. So this is the hard part. If I make a circle, all right, and I have a particular radius on the circle, let's say this is 0.50 meters. Nice and easy, 0.50 meters. Okay. Can you tell me what the diameter of this circle is? The diameter, 0.5 meters. Radius? Yeah. Okay, you double the radius, so a diameter then of 1 meter. Can you tell me the circumference? Bet you can. All right. Circumference equals 2 pi r. Well, we already did twice the radius, and it equals 1 meter. So what's 1 meter times pi? In this case, the circumference would be 3.14 meters. Lovely. What if I told you I'm spinning a yo-yo around a circle whose radius is 0.5 meters, and I'm spinning it 3 times per second? Well, how do we do that? What is my radial velocity, or just my velocity? We'd probably call it tangential velocity. My velocity tangent to the curve. What is that velocity if I'm going 3 times per second around that? Well, 3 times what? There's my circumference. So each time around is 3.14 meters, right? So velocity, in this case, is going to be 3 times per second, 3.14 meters. So what's 3 times 1.4 meters? You're doing that distance every single second. That's all. So if you have to calculate velocity, you need to get back to geometry. You need to figure out the circumference of the circle. If you can figure out the circumference of the circle, see how many times per second they're asking that be repeated. That is going to be your velocity. So here it's going to be 9.42 meters per second would be your velocity around that circle. All the other stuff is Gibbons formula S&S. Should be fairly straightforward to do, and I'll let you have at those problems. All right. Well, that's uniform circular motion. We're doing it around the sun. Sun's doing it around the Milky Way galaxy. Moon's doing it around us. The Earth is spinning, so we actually have uniform circular motion around the Earth. Interesting to think of how many different ways we are moving with uniform circular motion while I stand here and talk to you about it. That's some physics. Bye-bye.